In this video, we're going to apply the second law of thermodynamics to help us analyze the work produced by a heat engine. Okay? And so what we're dealing with here is a heat engine that takes in heat at a rate of 1,000 kilojoules per minute, and that heat is coming from a hot reservoir that's 800 degrees, or 800 Kelvin. Okay? The engine also deposits heat into a low temperature reservoir that's at a temperature of 300 Kelvin. Right? And so this problem tells us that shaft work is produced by this engine, and assuming that the entire process is reversible, what the problem asks us to do is determine how much work is produced by the engine, and also what is the rate at which heat is emitted to that cold reservoir. And so based on this problem statement, please pause the video here and draw out a schematic describing this process. And so based on this problem text, we could draw a process flow diagram that looks like this, where we have heat from a hot reservoir at a temperature of 800 Kelvin. QH is 1,000 kilojoules per minute. Goes into an engine. The engine produces shaft work, essentially. And not all of the heat that's put into the engine is converted to shaft work. Some of it is deposited to a cold reservoir that's at a temperature of 300 Kelvin. And what we want to find is the work that is produced by the engine, and also what is the heat flow rate to that cold reservoir. We essentially have two unknowns, and so that means we're going to need two equations to solve for everything. Okay. For our analysis, before we begin with the balances, we're just going to make a few assumptions. The first thing that the problem just tells us to assume is that the processes that are going on in this engine are reversible. Okay, and so that means that any sort of entropy generated term is going to be equal to 0. Okay. We could also assume that the engine operates cyclically. And so that means that effectively the system's kind of at a steady state, where du dt, dh dt, and ds dt, all those things are going to be equal to 0. Okay? Alright, and then the last thing we'll assume is something we assume in almost every thermal problem, that changes in kinetic and potential energy, those are going to be negligible. Alright? And so those are the assumptions we're going to make. Now let's move on to our balances. For the material balance, we're dealing with essentially a closed system. There's no mass crossing the system boundaries. So we have no reaction. It's a closed system. Therefore, accumulation is going to be equal to 0. And so that tells us that any mass in the system at the end is equal to any mass that was there initially. And we could just think of that as some sort of mass. In fact, since it's a closed system, it's not a mass flow rate, it's just mass. Okay? So our material balance, doesn't really tell us that much useful information. So let's move on to the energy balance. We could start with the rate form of the energy balance. Okay? We don't care about changes in kinetic or potential energy. And also, because this engine is operating cyclically, du dt is also going to be equal to 0. Alright, for the work, we're only really considering shaft work, so I'll replace that with shaft work. And for the heat, there's two types of heat that we're going to be dealing with, QH and QC. Okay? And the shaft work here. And notice, I'll point out here that I put a positive sign on QC, right? Because for right now, we're not assuming any sort of directionality with QC here, right? That's going to pop out when we actually calculate the QC value, okay? So for now, I'm keeping a positive sign there. In any case, these Q's and this S, that sum, that's going to be equal to 0, okay? We can't do anything with this now because right now we have two unknowns. We have QC and WS. And so what I'll do is I'll save this equation for later. I'll call this equation 1. All right, And so with our energy balance, we don't have complete information yet. So the next thing I'll do is just move on to the entropy balance. Once again, we'll use the rate form of the entropy balance, where we now have these Q dots over TIs and we have two of them, and we also have a SGen dot term. We're assuming the system is operating reversibly, so that's going to be 0. And then we could add in the actual heats we're dealing with in our system, plus QC TC. Now, because this engine's operating cyclically, once again, this ds dt is going to be equal to 0. Okay? And so, the only unknown we have in our statement right now is QC. So one unknown, one equation. So let's solve for QC. What we get is that QC is equal to negative QH times TC over TH. Okay? And so if we plug in all the values there, what we get is that QC is equal to negative 375 kilojoules per minute. Okay? So that negative sign is important because this tells us that this is heat leaving the system. Right? So this matches our physics or description of what's going on in the problem. QC is leaving the engine, right? And so it should be negative. Okay, and so we have QC, and then what we could do now is we could go back to equation 1, and we could solve for that shaft work. Okay, we could plug in the QC value directly, but instead what I'm actually going to do is I'm actually going to plug in the equation we got for QC back into the energy balance. Alright. And then I could factor out the QH, and I get this sort of simple looking equation for the shaft work. Right? And so we could just go out and solve for the shaft work. 1 minus 300 over 800 Kelvin. And what we get is that shaft work is minus 625 kilojoules per minute. Okay? And once again, this negative sign is important because this tells us that the shaft work is leaving the system, which is what we want. This is work that's leaving the engine. Okay? All right, and so just, using a combination of the energy and entropy balances, we could solve for both the heat going to the cold reservoir and the shaft work. One other thing I actually want to point out in this equation is I want to define a new term. And so in that energy balance, after we combined the first and second law, we got a pretty simple looking equation. And we could further rearrange that equation to give us something that I call efficiency, which is this eta symbol here. It's not an N, it's the Greek eta symbol. And so eta, that's typically what we use to describe efficiency. We could define it as the negative of the shaft work divided by QH. Okay? And so from our energy balance, take a look back here. Shaft work was here, and we had negative QH here. So all we're doing is just moving this underneath here. And so what we get is that ratio is just equal to 1 minus TC over TH. And so for our system that we were dealing with, we have TC and TH. And so then our efficiency is 0.625, or otherwise 63%. And so this tells us, at least physically, that 63% of the heat that was put into the system is actually converted into shaft work, right? And 37% of that heat is dumped into the cold reservoir, right? And so this defining this sort of efficiency term is very useful for understanding, how irreversible or 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 how efficient a process is, right? And the interesting thing here is we see that only 63% of the heat energy is actually converted into shaft work. But that's kind of weird because one of the assumptions we made about our heat engine was that uh, all the processes are acting reversibly. Okay, and so we're gonna kind of talk more about this idea of efficiency later on in chapter 5. But what I want to say now is that this efficiency that we defined here has a special name. This is known as the Carnot efficiency. Specifically, it's the efficiency you would get from a Carnot cycle, right? And so we would abbreviate it as eta Carnot. And this Carnot efficiency is the maximum efficiency that you would get, that you could achieve, that can be achieved by a heat engine that has a given TH hot reservoir temperature and cold reservoir temperature. So if you just know these two values, you could calculate this Carnot efficiency. Okay? And we'll talk more about this in chapter 5.